Okay, so let us talk next about uh, addition to reductions, namely self-reductions. And self-reductions are also known as recursions. So let's go over what recursions are. And hopefully you guys have a pretty good idea of what they are just from your prior intro programming courses. But now we're going to take a more theoretical approach to recursion. Okay, so as discussed previously, a reduction reduces one problem to another problem. A recursion is a special case of a reduction where we reduce a problem to a smaller instance of itself, i.e., it is a self reduction. So we could reduce a problem of size n to one or more problems of size n minus 1, n minus 2, anything like that. We could reduce a problem of size n to two problems of size n over 2, as we'll see with merge sort. And for termination, we'll have to have a base case, right? Because if we continuously reduce the problem, the reduction has to end sometime, right? We have to eventually get to a point where we do some work and then build our way back up. So of course, that's why we need a base case. So this concept of reducing a problem, of having a base case, having sort of the smallest version of the problem, and then building up from that base case into larger and larger and larger portions, into larger and larger instances of that problem, what does that remind you of? It reminds you of induction, right? It reminds you of induction in mathematical proofs. So recursion is basically induction for computer programs. Okay. So recursion is a very powerful and fundamental, I will say, fundamental technique. And this surprises me that how many students sort of go through up until their junior and senior year without a strong grasp on recursion. Hopefully that won't be you guys. Hopefully you guys already have it mastered. But just in case you don't, we are going to go through it here. It is the basis of many, many computer algorithms, namely divide and conquer, dynamic programming, enumeration, branch and bound. So that enumeration, remember in the earlier part of the course, we discussed sort of grammars and how you could get strings from grammars, right? So the way to enumerate all the strings in a particular grammar is to use a recursive function. You basically need a recursive function in order to enumerate grammars. And several other classes of greedy algorithms also go through recursion. And there's many more. There's many more algorithms that use recursion. Recursion is often not seen a lot in production code simply because it is a risk. If recursion is not written well, it could be a huge slowdown, or it could blow up. It could blow up, and then the computer won't be able to handle it. So I will admit that a lot of code does not use recursion in its production code. However, it is the basis of a lot of computer algorithms. And then once you build a recursive algorithms, then you can make optimizations to make that algorithm not require the use of the program stack, for instance, right? Also, coincidentally, you will notice that in a lot of sort of GPUs, I'm not sure if they added this feature to CUDA yet, but when I was learning CUDA about 10 years ago, CUDA didn't support recursion. There's a lot of novel computer architectures that don't support sort of a program stack, right? So that's why in a lot of production code you don't see recursion. But what's important is that you still need to design an algorithm that uses recursion. And so even if you don't have a program stack, you could go back and sort of emulate a recursive algorithm, a recursive function using a actual stack, assuming your architecture supports that. So as we discussed, recursion is pretty much the same thing as induction. And we also need to be able to analyze our analyze our recursive functions. And a function, i.e. a mathematical function that refers to itself, i.e. something of the form t of n is equal to some function or some other t of a function of n. This is what's known as a recurrence, right? So a recurrence describes a recursive function, and recurrences are everywhere in mathematics, like literally everywhere. So that's why this is so important. Okay, so hopefully I've sort of gone on long enough on my soapbox, and let's start discussing actual examples of problems that need recursion. And the big one, the basic hello world problem for recursion is what's known as the Tower of Hanoi problem. Okay, and so what is the Tower of Hanoi problem? The surprising thing is that, again, when I first learned programming in high school, actually, this was the first algorithm. This was basically one of the first problems they taught me in order to motivate recursion. And then I get here, and the first time I teach 374, I basically brush over the Hanoi like very quickly, because I assumed like it's everyone had known it, right? I learned it in high school, then I had to go through it again in college like multiple times. So given that given that this is a junior and senior course, like I was like, okay, well, everyone knows this, so we could blow through it. And boy, were the students that semester angry, because I gave a problem based on Towers of Hanoi, and not a lot of people had experience with it. So I think one of the reasons why this may be is the switch from learning to program in C versus learning to program in Python. In normal general purpose languages, you become intimately familiar with the program stack. But in scripting languages, the program stack is often abstracted away, meaning recursive functions don't come up as much. But anyway, but the Tower of Hanoi problem, again, it's one of those things you won't ever see in industry code. It's a very cute problem. You might see it on a job interview, but it is basically a super important problem for testing how well you understand recursion. Okay? And so the Tower of Hanoi problem is simply that you have a pyramid of golden discs. Okay? And these golden discs are very fragile. Okay, I'm giving you sort of the descriptive flavor that professors usually tout out with the Tower of Hanoi problem. You have these golden discs. You have this tower that is maintained by some monks in Hanoi, and then you have these golden discs. And the thing is, these golden discs are very, very fragile. If they're not fully supported, okay, if you put, for instance, a golden disc if you put a bigger golden disc on top of a smaller golden disc, like so, then immediately the larger golden disc would break and fall off, right? So the monks that maintain the quote-unquote tower, or it looks more like a pyramid, but the monks that maintain the Tower of Hanoi have this special tool that as they're moving each disc, they could support it completely, but eventually they got to put the disc down, right? So they got to put the disc down in a way that the largest discs are completely supported, have a complete surface under them, right? In other words, they gotta make sure that the order of the discs always goes from largest up to smallest. Okay? So the question is, how do we move this tower from one peg, let's call this peg 1, to another peg. Let's call that peg 3. Now, the key here is that the monks are actually, they have a tool to move each individual disc, but they can't move more than one disc at a time. I know, a lot of constraints, okay? But again, this isn't an actual thing. This is just sort of a computational game. Okay, so the monks could move each disc one at a time. The discs are very fragile, so they always have to be on a peg in decreasing size, in order of decreasing size. And the monks want to move the tower every so often from one pole to another pole. And in their monastery, they have exactly 3 poles to move the discs, right? So the question is, how do you move the discs? Is there a way to move each disc one at a time to get from pole 1 to pole 3? Okay. So what's our strategy? So whenever I deal with problems like these, I like to just sort of try some things out. Okay, so let's just experiment with the tower. Okay, we have 3 poles. 1, 2, 3. Okay, and let's start off with a small number of discs. I'm going to start off with 3 discs. So is there a way to get these 3 discs from pole 1 to pole 3? Okay, and I think this is doable. Okay, I think if I take this disc, the smallest disc, and move it to tower 3 here, then I'll take the second smallest disc, the middle disc, and move it to tower 2. Yep. Then I take the smallest disc and move it on top of the middle disc, back to tower 2, and then I take the largest disc and move it to the end, like so. Then I'll take the smallest disc. I got to move it sort of out of the way to put the middle disc on top of the largest disc. And then finally, I can move the smallest disc on top. Okay, so if you have 3 discs, it definitely is possible to move them from any tower, assuming you have 3 pegs. Okay, so that's the Tower of Hanoi problem. I never once had to go from put a larger disc onto a smaller disc, like so, because that will cause this yellow disc to break, right? And we don't want that, right? So we maintain the condition that always larger discs on the bottom to smaller discs on the top. And we were able to move 3 discs from pole 1 to pole 3. All right. Now, what about if there are 4 discs? What do we do in this case? Well, this one is a hard one, right? I think maybe we should move the smallest disc here. We should move the yellow disc here. We should move the smallest disc here. We should move the green disc to the middle. We should move, now we would like to be able to move this large disc to pole 3, but there are 2 other discs in the way, right? So we got to get the smallest disc out of the way. We got to get the yellow disc out of the way, maybe onto pole 2, smallest disc back onto pole 2. And then of course we can move the largest disc onto pole 3. Then we can move the smallest disc onto pole 3. Then the yellow disc onto pole 1. Then the smallest disc onto pole 1. Then the green disc onto pole 3. Then the smallest disc onto pole 2. Yellow disc onto pole 3. Smallest disc onto pole 3. Bam. I can't believe I remembered to do that in one shot. But the point of this whole exercise is that yes, it is possible to move 4 disks from pole 1 to pole 3 using only one other pole. Okay, and making sure not to damage any of the disks, right? And in fact, we could go for an infinite number of disks, right? Assuming n could go to infinity, and the truth is we could always manage to move the tower that is n disks large from 1 to pole 3. Okay, but how did I do that? How did I manage to move all these disks from pole 1 to pole 3? And I could tell you, I did not memorize the moves. Okay, I did not memorize the moves. I just have one very, very simple thing in mind. Okay, let's go back here and let's actually go to disk 3, the 3 disk here, and let's reset the problem. What's the observation that I did when I moved them all? Let's try this again. I move, I move the smallest disk to 3 in this case, then the medium disk to 2, then the smallest disk to 2, and then the largest disk to 3, then the smallest disk to 1, largest disk, medium disk to 3, and then smallest disk to 3. Okay. So what did you notice there? What did you notice there that was true here as well? How was I doing it? How was I moving the n disks from 1 to 3? Let's do it again. 1, 2, 3, 2 to the middle, smallest to middle, then largest disk to 3, then smallest to 1, middle to 3, middle to smallest to 1. Well, the key observation is that in order to move n disks, from tower 1 to tower 3, you have to first move n minus 1 disks You have to first move n minus 1 disks. Sorry. You have to first move n minus 1 disks from pole 1 to the intermediate pole, and then move the largest disk from the beginning pole to the end pole, and then you move these disks from the intermediate pole to the end pole. Okay, so what we're doing, let's write this out. Let's write this out and say, in order to move, let's call a function called get. Okay, and get takes in the following information. This is n, which is the number of disks, and then, or the number of disks that need to move. Then we have a S, which is the begin pole. The pole that all the disks start out on. We have T. Let me make sure I'm getting the nomenclature right. Oh, yeah. We have T, which is our temporary pole, temp pole. Also, we could call this intermediate, mediate pole. And then we have D, our destination pole. Okay, so what do we do here? We need to get 3 disks from pole 1 to pole 3. And the intermediate pole is 2, right? But in order to do that, we need to first get 2 disks, these top 2 disks, from pole 1 to pole 2. And then here's the key observation. Since we are only moving these top 2 disks, it doesn't matter that the largest disk is still on 1. That doesn't matter, because we could still put either the purple disk or the orange disk on pole 1. They won't break, right? As long as we maintain that we're only moving the smallest end disks, then we could safely ignore the larger disks that are in the middle of the transition. So in this case, we simply need to get the top 2 disks from pole 1 to 2 using intermediate pole 3. And then we need to move disk N to pole 3. And then we need to get the 2 smaller disks that are now on the intermediate pole 2 onto pole 3 using 1 as a intermediate disk. Okay, so what will this function do? Let's evaluate this out a bit. Let's extend this out a bit. What does get 2132 do? It basically says it needs to get disk 1 to pole. It needs to get disk 1 to the intermediate pole. It needs to get disk 1 to the destination, pole 2. Yep, it needs to get disk 1. And actually, I won't write that down, but it will get disk 1 to pole, the intermediate pole, which is 3. Then it will move disk 2 to pole 2. Then it will get disk 1 from 3 to 2. Right? Which is exactly what we did. We simply took disk 1, we moved it to 3. Then we took disk 2, moved it to pole 2. And then we took disk 1 and we moved it to pole 2. Simple as that, right? So so the point of all of this is that this problem, while it appears very difficult, and it does, the problem complexity explodes as the number of disks explodes, as we saw here, as we saw with 4 disks. Even though it seems like a complex problem, we only need some basic logic. We only need some basic logic to basically find the moves that we need to get n disks from a beginning pole to a end pole using some intermediate pole. Okay, and that is our basic Tower of Hanoi recursive function. So we move the n-1 disks from the beginning pole to an intermediate pole. Then we move the large disk from the beginning pole to the destination pole. And then we move the intermediate disks from the intermediate pole down out to the destination pole. Okay? And so, as we noted earlier, this algorithm works by saying this algorithm works like so. We have an algorithm that takes in 4 inputs: A, the number of disks, the n disks that we need to move, the source pole, the destination pole, and some temporary pole in the middle. And all we're saying is that if there are some disks that need to move, then we move n-1 disks from the source pole to the temporary pole. We move the largest of the n disks from the source pole to the destination pole. And then we move the n-1 disks, which are on the temporary pole currently, we move them to the destination, using the source pole as an intermediate value. And so this works because, again, we're only moving the n smallest disks. So even though it's very possible that, oh, sorry, let me draw something that's slightly more attractive. Ooh. There we go. Even though we have 3 poles, let's call that, and let's say that we have disks, we have very large disks that are in all array of distribution across the thing, right? We have some very large disks, but as long as we're moving the small disks, as long as we're moving smaller disks, these larger disks don't really matter. These larger disks don't really matter. As long if we're only moving these smaller disks to some pole, it doesn't matter what larger disks are in waiting, right? As long as we're maintaining the relationship, which we are. This function never violates the condition that the disks are stacked from order of largest to smallest. Okay, so this is the Hanoi problem, the most basic form of recursion. And so the question is, how fast does it run? How many moves do we need in this case? How many moves do we need to move n disks? And so we know that we described the number of moves that we need to move n disks. The number of moves that Hanoi n invokes is t to the n. That's how we write our recurrence. I'm not sure where t actually comes from, but typically that's the notation that mathematicians use to describe a recurrence, t. Or I should say that computer scientists use to describe a recursion, t. So we have this t to the n, we have some function that describes this recursive function. And so what does this function equal? Well, this function basically calls 2 of itself for n-1 disks. This is t to the n-1. This is t to the n-1. And this is also t to the n-1. And this function does 1 move. Okay, so we get what's known as a recurrence that takes exactly, that's described as t to the n is equal to 2 t to the n-1 plus 1. Okay, so how large is this recurrence? Well, let's do it out, right? Let's expand the recurrence. We know that if t to the n equals 2 t to the n-1 plus 1, Then we could expand it out because we know t to the n minus 1 is equal to 2 times t to the n minus 2 plus 1. So we take this and we say 2 times 2 to the t to the n over 2 plus 1, which is what we get here. So 2 squared t to the n minus 2 plus 2 plus 1. And again, we know that t to the n minus 2 is equal to 2 times t to the n minus 3 plus 1. So we plug that in here. 2 to the squared to the t times 2, times 2 to the t to the n minus 3 plus 1. That all that times plus 2 plus 1. And then you factor that out and you get 2 cubed t to the n minus 3 plus 2 squared plus 2 plus 1. And this is, of course, 4. Okay? So you expand this out and you get, if you're smart, you get a possible summation, or you get a summation, which is simply the sum of, oh, actually, let's leave that alone. You get a variable that's described by this function, and if you're clever, if you're very clever, you will recognize what this equals. What is this? I will give you a hint. Think of a binary number, 1, 1, 1, 1, 1. What is this equal to? This is equal to 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3 plus 2 to the 4. Or if we add 1 to this number, 1, 1, 1, 1, 1, we get 2 to the 5. So this whole thing, let's say we have an n-digit binary number, is simply equal to 2 to the n plus 1, 2 to the n, 2 to the n minus 1, which is what we get here. Okay, so this recurrence right here is simply equal to 2 to the n minus 1. That is how many steps it would take to do the Tower of Hanoi problem, right? So if n is 3, that's not too bad, right? If there are only 3 disks, then we get for n equal to 3, then it is 2 to the 3, which is 8 minus 1, which is equal to 7. Not too bad. That's what we saw before. However, if n equals 4, then 2 to the 4 minus 1, which is equal to 16 minus 1, which is equal to 15. Bit more, right? But let's verify this 7 real quick before we move on. If we take these right here, okay, there we go. Let's count it out. 1, 2, 3, 4, 5, 6, 7. Bam. There we go. Our recurrence works. So that is the Tower of Hanoi problem. It sounds complicated. That's what the beauty of the Hanoi problem is. It seems like a super complicated thing. And if you try to work through it with examples, you would become overwhelmed by 5 disks by the time you reach 5 disks, right? But if you're able to see the logic of what you're doing, that in order to transfer 5 disks, you got to first transfer 4 disks to an intermediate pole, and then transfer the 5th disk to the destination, and then transfer the 4 disks back there. If you're able to see that sort of logic, then the recursion function writes itself. And then, as long as you trust the computer, as long as your logic is correct, and you trust the computer, then the problem can be solved super simply. Okay, so that is the hello world of recursion. And so next we'll discuss some other recursive algorithms. All right, see you soon.